So I already said to you, this is probably, by the end of this, you're going to be going, wow, I just learned an awful lot. Part of it is, unfortunately, the rules for naming and writing formulas, they're not how I would have designed them if I was trying to make it as simple as possible. They kind of have evolved over the 150, 200 years of chemistry, and sometimes you'll go, really? And I'll just say, that's the way it is, because I'm not in charge. I wish I would not do things this way. Anyways, turns out an atom is the smallest part of an element. What are the elements? Your periodic table. Atoms combine to form compounds. And the smallest part of a compound is called a molecule. So a molecule is the smallest part of a compound. So we just finished writing some chemical formulas. There was the Mg2, those things. Those would be compounds. Those would be molecules. If you put a bunch of them together of the same thing, we call it a compound. Put your pencils down. Hopefully this little video is review. So all compounds have two things, a name and a formula. You're going to have to get familiar with both, and you're going to have to be able to go from one to the other. If I give you the formula, I want you to give me the name. That's usually the easy part, but not always. If I give you the name, I want you to give me the formula. That's usually the more difficult part, but not always. The name is generally composed of the names of the elements in the compound. In other words, hydrogen fluoride contains hydrogen and fluorine. With some exceptions, water, well, that doesn't sound like hydrogen and oxygen, but we know what it is. So the formula uses the element symbols from the periodic table. And it tells, and here is the key thing, I'm going to do this in red, how many atoms of each type are in one molecule. Tells you how many of each atom you would need to form one of that particular compound, one molecule of that particular compound. It says do activity 3-2A on page 84. Don't bother opening, I have it here. I'm going to pause the video. Is there a spot where I left you room for where it says what two rules did you discover?
Yeah.
You know what? First rule, what comes first, Drew?
No.
And then the second one, change the non-metal ending to "ide." So suppose I wanted to combine potassium and oxygen. What would I call it? Potassium oxide. Now, it doesn't tell you the formula, but that's how you get the name. Suppose I wanted to combine magnesium and phosphorus. It'd be what? Magnesium phosphide. Okay. It sadly gets tougher. So, always write the naming rules. This is probably what I had. Always write the name of the metal first, and always change the ending of the non-metal to "ide." Do I have these examples in your note? You know what, Mr. Duff, why don't you get a copy of the notes so you can kind of see what you gave her? That would make more sense. I didn't include this in your notes. This is just for us to think. Iodine and copper, which one would I say first? In fact, if I wanted to combine iodine and copper, what would you call it? Copper iodide. What about zinc and oxygen? Zinc oxide. What about fluorine and magnesium? Magnesium fluoride. Okay. By the way, that's why it's fluorine on the periodic table, but in your toothpaste it's called fluoride. Oh, I learned something new. I kind of wondered. So what will the ending of the following elements become? Fluorine becomes fluoride, oxygen becomes oxide, nitrogen becomes nitride. Okay. So, name the following compounds. You guys have room on your sheet as well. We'll do it right here. What would you call AgCl?
Silver chloride.
Sliver, Mr. Dewick, let's try that again. Silver chloride. What would you call ZNO? You won't call it ZNO anymore. You'll call it zinc oxide. I think you're right. Really, it's not, but I'm... What will you call CaCl2? Calcium chloride. Nope. Someone said calcium chloride too. The numbers don't appear in the name. What will you call MgF2? Yep. This is easy. Sadly, it's going to get tougher. I'm picking very careful, easy ones right now. Yep. Mr. Dick, will you be fussy on spelling? A little bit. I think the names are on your periodic table, so I'm going to expect you to spell like magnesium correctly. I think that's fair. AlS3. Aluminum sulfide. Or if you're in Britain, aluminium sulfide, which is actually the correct way, but we don't say it that way in North America, so okay. BAI2. Yeah.
Barium iodide.
Now, what do you notice about all of these examples that I gave you? What do they have in common? What's the first element? These are all maybe you might want to make a little note in the margin. The rules for covalent are totally different. In fact, in Science 10, when we start doing both, Mason, I always taught my kids, whenever you saw a chemical formula, before you did anything else, the first thing you always ask yourself was, is it ionic or covalent? That was more important than anything else because that gave you totally a different set of rules if it was covalent. I might do covalent with you guys this year. I don't know yet. Ion charge says this. We have learned that atoms gain or lose electrons in set ways to get a full outer shell. This is represented by the ion charge. Do number 2 and number 3 on your worksheet, remembering the change in the endings after nonmetals to "ide," and then answer the questions immediately after number 3. So I'm going to fill in the first couple, and then I'm going to let you do the rest. I'm going to pause the video, and I'm going to give you folks about 5 minutes or so. So you have a little chart. I'm going to do barium. What's the symbol for barium? Is it Ba? What's its ion charge? Now, that's nothing new. Scooch down to chlorine. What's the symbol for chlorine? Cl. What's its ion charge? Or you put 1- if you want to. Now, I couldn't tell you this last unit, but whenever you were drawing ions and they were non-metals, when I said to you draw a chlorine ion or a fluorine ion, what I really could have just said is, could you please draw chloride? If it ends in "ide," it's going to be the ion. Then also answer these questions. I'm going to give you about 3 minutes. I think you can get it done in 3 minutes. I think the answer is hopefully kind of obvious. So you said calcium Ca, charge 3 plus, magnesium Mg, or calcium 2 plus, magnesium Mg, its charge 2 plus, potassium K, its charge plus, silver Ag, I always have trouble with that one, and its charge, sorry, plus, sodium, charge plus, zinc. Sorry, what was the charge on silver? See, this is where you notice silver is way off to the right, and I told you as you get further, the rules break down, because normally it's everything in the first column has a charge of plus. How come silver has a charge? It just does, okay? Trust me. The more interesting ones are the bottom here. So fluorine, F, yes?
Yeah.
Minus, what do you call it? Fluoride. I minus iodide. O, 2 minus oxide. S, 3, no, 2 minus iodide. Sorry, sulfide. Iodide, sulfide. Then we had some questions. So the ion charge that forms on all alkali metals is plus. The ion charge that forms on all alkali, you know what? This is a typo. It should say alkaline. You know, I didn't catch that. Yours does?
Yeah.
Oh, and my pen just stopped working for some reason. Okay. Is what? 2 plus. The ion charge that forms on everything in column 16. 2 minus. Someone else showing up late? Mr. Dewick, yeah, Cole. Does column 16 have a name? Probably. I don't know what it is, though. But most columns have a special name. Anyways, the halogens, column 17, that's 1 minus or just minus. And the ion charge on the inert or noble gases is nothing, 0. So what have we learned so far? If you give me the formula, I can name the compound. The order of the elements is important. Metal first, then non-metal, and then the "ide" rule, change the ending. We can determine the ion charge from the periodic table. What do we still need to learn how to do? How to determine the formula from the name. So, rule number 3. When ions combine to form compounds, they will combine so that the ion charges are all balanced or equal to 0. In other words, if I have 3 positives, how many negatives do I have to have? 3. Okay? If I have 5 positives, I have to have 5 negatives. Is there anything with 5 positives? As you get further down, there's all sorts of weird stuff going on there. The ion charge is the charge that forms on an atom when it gains or loses electrons. The ion charges can be found on your periodic table. Where can you find the ion charge on the periodic table? Top right. So do you have to memorize the ion charges? No. Mason, you have to know where they are. And because it's a number, don't get it confused with the atomic number, which is top left, or the atomic mass, which is bottom middle. Yeah, there's lots of numbers. Keep them straight. I don't have a good way to keep them straight except to say keep them straight. Although the ion charges have pluses and minuses, which helps because you know it's a charge. When an atom loses electrons, the ion will have a positive charge or negative charge when you lose electrons. Now, this is the tricky part. This is where I say Benjamin Franklin got the charges backwards. He should have called electrons positive. Also because it's electrons that are doing all the moving, and it'd be nicer to think about positives moving around. Right now, when you lose negatives, You're positive. When an ion gains electrons, even though it's gaining electrons, it's gaining negatives, so it has a negative charge. The chemical formula tells us which atoms are present in a compound and how many of each one there are. And here is the key idea. It turns out that ions combine in set ways or specific ways to form compounds. And then I have some just thinking, this is not in your notes. If you had to determine the formula of sodium iodide, what would you write? Well, sodium. What's the charge on a sodium ion? Iodide. What's the charge on an iodide ion? How many of each of those would you need to have a lovely, balanced, happy compound? 1 and 1. So you could just write NaI. Technically it's 1 and 1, but just like in math, when we don't put 1s in front of x's, we don't bother putting 1s there. How about calcium iodide? Well, what's the charge on calcium? The charge on iodide, that? What do you think? So how do you know there needs to be a 2? Look at the ion charges. Now, I'm going to give you eventually a shortcut, but for what it's worth, Alyssa, I'm arguing you can kind of do this intuitively if you're okay at math. You can kind of just do the arithmetic. Yeah? In theory? Good. Determining the formula. Do I have this in your notes? Yes, I do. So, since the overall charge on an individual molecule of a compound is 0, the positive charges must balance the negative. So, if a metal ion has a charge of +2 or 2+, it can form a compound with either one non-metal with an ion charge of -2. What's the math behind that? Well, 2+ plus 2- is 0. Or it can form a charge with 2 -1s. 2+ plus a 1- and another 1- equals 0. This is just for you to think about. You don't need to write this down. How could 2+ combine with a 3-? How can you get those to cancel? How many positives will you really need grand total? 6. How many negatives will you really need grand total? 6. So you'd need 3 of the 2+ and 2 of the 3-. So a little bit of arithmetic still, but it can be done. It may help to think of it as if ions have the same number of hooks as the size of their charge. So for example, a fluorine F- has 1 hook. A Ca2+ has 2 hooks, and all of the hooks have to get connected from a positive to a negative. So there's these things called hook diagrams. I can't draw and I'm not visual. Martin, I find the math works well for me, but some people like the visual analogy. So KBR, here's a K plus, it's got one hook. BR has one hook because it's a 1 minus. All the hooks are hooked onto other hooks. I realize that's a lot of saying the word hook, okay, but that works. So calcium, you could think, here's calcium 2 plus, and you could think of it as having 2 hooks. Here's oxygen, which is 2 minus, and you could think of there's an oxygen element having 2 hooks. Are all the hooks hooked up? Then that's your chemical formula. This will work as CaO. Calcium oxide. I'll make this a bit bigger here. What about calcium? How would I say this, by the way? Calcium chloride. If you want to visualize why it's CaCl2, you have calcium, which is 2 plus. You have chloride, which is 1 minus. And so calcium, you can think that it's got 2 hooks. Well, chloride only has 1 hook. Oh, I need another chloride. There, now we're all hooked up. So some of my students, Nick, find this visual approach good. Doesn't work for me because you may notice I can't draw. I'm not a visual learner. How would I say this? Na2O. How would I say this? Sodium oxide. Okay. It turns out Na has plus, oxygen has 2 minus, so I always draw the bigger one first. So it looks like oxygen wants 2 hooks. I guess sodium can take 1 hook, and another sodium can take 1 hook. And there is your kind of a rough picture of what's going on here. These are called hook diagrams. Is that okay? Turn the page. Try drawing on your own. Oh, how would I say ALI3? Aluminum iodide. Try drawing a little hook diagram picture. I'll do it up here. If you don't want to write all the charges, if you think you can just go to the sketch and see why it is, you can. That's great. Something like that. I had a bunch more for you to draw, but if you're getting the hang of this, I think I'm going to skip the next few. You may have picked up, Josh, I'm not a big fan of the hook diagrams. For me, they don't wrap my brain around. For me, I do the arithmetic. I'm a math guy. So if you want to try these ones, you can on your own. Formula activity, I can't remember what that was. I think that's from another teacher. I stole this PowerPoint from them. Another way to think about this, hang on, what do I want to write here, Mr. Dewick? Oh, easier. But also easy to make a mistake. Oh yeah, the aluminum, that one, yeah, you 2 aluminums, each with 3 hooks, and then 3 of the other one, each with 2 hooks. One of them has to have a hook from one aluminum and the other aluminum. You want me to do that one real quick, Brian? I can.
Yes, please.
Okay, so it's going to be two aluminums. Here's Al. Each one has 1, 2, 3 hooks, 1, 2, 3 hooks, and then there's going to be oxygen, 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 and it's going to be 1, 2 hooks, 1, 2 hooks, 1, 2 hooks. Something like that. Is that okay? Okay. So another way you can fill this in, another way to think of this, which is way easier, but it's also easier to make a mistake, is called the crisscross rule. What's the crisscross rule? Well, what you do is you write out the ions with their charges. As an example, when we had M, G, and P. What's the charge on magnesium? What's the charge on phosphorus? The crisscross rule says if you want the formula, this number ends up down there, and this number ends up down there. Can you see why we call it the crisscross rule? Except you just ignore the negatives and positives. In other words, you want the chemical formula for magnesium phosphide, it's going to be Mg with a 3, P with a 2. That's how I do them in my head. But you know what? It's really crisscross, and then you have to reduce to lowest terms. Sometimes you'll end up with something that can reduce. If there's like a 2 and a 4, that's really just a 1 and a 2. So, you move the number, but not the plus or minus, from one ion to the subscript of the other ion. Oh, remember, you don't need to write a 1 if there's only one ion. So let's try the crisscross shortcut to combine aluminum and oxygen, aluminum oxide. What's the charge on aluminum? What's the charge on oxygen? The crisscross rule says, you know what? The 2 is going to end up there. The 3 is going to end up there. The chemical formula is Al2O3. I'm kind of, Alyssa, 50-50 between whether this is a good shortcut or whether it's just easier to do it in your heads like we've been doing kind of intuitively. But if you want a system, there it is. We're going to pause here. Here's your little bit of homework. I want to give you 15 minutes.